So in the previous video, we introduced the valence bond theory of how covalent bonds are formed. We talked about how orbitals overlap from adjacent atoms. Orbitals overlap with each other, and that overlap causes sharing of electrons to form the covalent bond. And we ended with this slide by saying that Lewis dot structures can be a shorthand notation, a guide for a valence bond description of a molecule, along with taking a look at the orbital diagram, specifically for the valence electrons, for the atoms in the bonds that you're talking about. And so remembering that and looking at the orbital diagrams for, in this case, hydrogen and sulfur, we can easily see that in a molecule of H2S, that a 3p orbital from sulfur can overlap with a 1s orbital from hydrogen, and that can happen again with a second hydrogen to form a covalent bond. Those overlapping orbitals produce a electron and molecular geometry that matches with what is seen in nature and matches with what is predicted with the Lewis dot structure. And that's where we ended our last video. Sometimes Lewis dot structures, along with orbital diagrams in and of themselves, do not sufficiently explain the kinds of bonding and molecular geometries that we see. What do I mean by that? What you see here in the upper left-hand corner is the Lewis dot structure for CH4 for methane. And if we were to do the Vesper notation for methane to determine the molecular geometry skills that we learned in chapter 8, we would say, this molecule is AX4. AX4 has a tetrahedral molecular geometry with a predicted bond angle of 109.5. And that of itself matches what is actually seen. But things get a little confusing when you think a bit about the orientation of those actual p orbitals that are on the carbon. And things get even a little more confusing when you think about what the electron configuration is for an atom of carbon, specifically looking at its valence electrons. So carbon, remember when talking about electron configurations in a previous chapter, the electron configuration for a carbon atom has as its valence electrons 2s2, 2p2. Well, looking at that, it's really hard to see how in the world can carbon form 4 bonds. Carbon has looking at just the atomic orbitals for carbon, carbon has 2 2p orbitals where some overlap could occur, but then it has a third p orbital that's completely empty. So how can 4 bonds to carbon occur? How can we get a bond angle of 109.5? Specifically, when you look at the orientations of the p orbitals, they're all 90 degrees to each other in these cartoons. So how can we reconcile valence bond and Lewis dot structure, or that Vesper AXE notation? How can we reconcile to each other? So it turns out we need another model. Yes, another model that goes hand in hand with valence bond theory. That concept still involves overlapping orbitals to form covalent bonds, but now we're going to think about overlapping atomic orbitals, those s, p, d, and f's, specifically s, p, and d for us. We're going to think about those atomic orbitals, and when they overlap, they produce something called a hybrid orbital. When you think of a hybrid, you think of a mix. We call them hybrid orbitals because of what's going to happen with them before they overlap with other orbitals. What does all that mean? Let's go back to good old methane, to show an example of hybrid orbitals. The definition of a hybrid orbital is an orbital that results from the sum of the atomic orbitals. Those hybrid orbitals are a set of orbitals that have lower, or that have in between energy from the atomic orbitals that they are comprised of. So for example, if I was, let's go back to methane, CH4. We said that for CH4, there should be four bonds attached to carbon. And as we saw in the previous video or previous slide, how can we explain that? Because the valence shell electrons for carbon, 2s2, 2p2. Well, we can think about the possibility of having 4 orbitals available for overlap with hydrogen if we were to take those valence atomic orbitals, the 2s and the 2p, and hybridize them. Specifically, what does orbital hybridization mean? It means that one of the, in this case 2s electrons, is promoted to a 2p orbital. And doing that, to do that promotion, these orbitals combine in a mathematical way to produce a set of orbitals that are in between energy between the 2s and the 2p. And so after doing that electron promotion and hybridization or mixing, we get 4 different orbitals. 4 because we have taken 1 plus 3 orbitals to get a total of 4. And these 4 orbitals, they have s character and they have p character. So these 4 orbitals are going to have a new address or a new designation. They're going to be called sp. And since we used 3 p orbitals in this hybridization, we're going to have the superscript 3. So doing this hybridization of carbon's valence shell orbitals gives us 4 sp3 hybrid orbitals. And why is that? Why would we want to do that? Well, now we have 4 orbitals that have a single electron that are available for overlap with the hydrogen's 1s orbital to form a covalent bond. So these hybrid orbitals, which are shown in this cartoon, you see they have some p character, mostly p character, but they have a little s character as well. So they've got these slightly elongated lobes. Okay. So now we can explain through, at least with methane, we can explain through these hybrid orbitals how and why that bonding occurs. Okay. So this concept of hybrid orbitals, we're going to use it for some more examples in the next video. Take-home message from this slide is that hybrid orbitals are a set or a sum of orbitals that are created when hybridizing or mixing particular valence shell atomic orbitals.